Okay, guys, so 9.2, we're going to look at this new concept called correlation, and we're just going to be dealing with correlation. So I need to give you some definitions first. So I told you that an example could be there is a correlation between how long you study and then your grade on the test. So that kind of gives you a general idea. Oh, my coffee's still on. Here's the mathematical definition. The correlation is a measure of how well a linear regression line fits a set of data. So, remember how yesterday we were doing the linear regression lines, which is your line of best fit? And so you have a whole bunch of data scattered all over, and we're trying to find the line that best represents all that data. Your correlation is going to tell you how accurate that line, or how well that line actually represents the data, okay? So sometimes, like remember on our graph yesterday, and I'm going to flip it over, so don't freak out. I'll give you back the definition in a second. So remember our graph yesterday and how this line was like super tight and it's almost exactly a line, and when we graphed the line through it, it was pretty close to all the points. That means if we were to calculate the correlation, it would tell us that the line of best fit had a strong correlation, meaning that it was a really, really good indicator of the equation for this line because it was really close to all of the points. Then we also graphed these 3 points. You guys remember these 3 points? Our line of best fit is going to go through all of them, but it probably wasn't as close as the previous line that we had graphed because these are definitely not collinear. Remember we talked about collinear? So the correlation between the line of best fit for these 3 points might not be as strong as the one for the other one, okay? So that's kind of what we're looking at today. So here's your definition again. Okay? We have 3 types of correlation. Okay? So there are 3 types of correlation that we're looking at. If all of your data kind of goes in an upward line, so it has a positive slope, or it's a positive linear or an increasing linear kind of look, we call that a positive correlation. Okay, so that's considered a positive correlation or association. It doesn't really matter. What if it's going down? What would you guys call that? Negative. So it looks very much like kind of what we're expecting. Now look at this one. So if we look at the positive, it's the y-axis on this one says grades on algebra tests, and this one, the x-axis says time spent studying. So the longer you study, the higher your grade on the algebra test. So that means it's positive. As one increases, so does the other. This one tells you y-axis is miles per gallon, x-axis is the weight of the vehicle. So as your vehicle gets heavier, you get less miles per gallon, so it goes down. So that would be a negative, because as one increases, the other decreases. That's why it's called positive and negative. It's not good and bad. It's just both are either increasing, or one is increasing and one is decreasing. And then this last graph that I'm giving you an example of is x-axis is IQ score, y-axis is height. Do you think those are related at all? No. And so if you look at all of the different points, they're not in a line at all. So we say that that is no association or no correlation. Okay. In your notes, what I want you guys to do is just do a sketch. It does not have to be exactly what is up here. Just give me an example of a positive correlated that looks similar to this, one of a negative, and one of no. You don't have to label the axes. You don't have to make it exactly like this, but just do a sketch of what's up here, okay? All right, so we have what is called, when we're talking about correlation, a correlation coefficient. So the correlation coefficient tells us how tight our line is, or how tight our data is in compared to the line of best fit. So the more linear or more tight our data is, the higher our correlation coefficient is going to be, because it's telling us that this is really, really correlated. Okay? So correlation coefficient. Last definition, and then we're all examples. The correlation coefficient is a value between 1 and -1, which indicates how close the data are, to forming a straight line, okay? So it's some number between -1 and +1, it can be any number in between there, to tell you how close the data are to forming a straight line. Something I need you to note, the closer the correlation coefficient is to 1 or -1, so the bigger the correlation coefficient is, the stronger the linear relationship, okay? The correlation coefficient is represented by the variable r. Don't ask me why it's r and not c. I don't know, but it's r, okay? Okay, so the first example, I'm going to give you different scatter plots, and we're going to determine whether the points have a positive correlation, a negative correlation, or no correlation. And then we are going to circle the given R values for each one that we think, based on the picture, it is. So let's look at A. I have this scattered data, and it's kind of going down. So would that be a positive correlation or a negative correlation? Negative. So I'm going to just write negative underneath. Okay, so then they give me 3 R values. Let me zoom in. Remember, R is our correlation coefficient. R equals 0.9, R equals negative 0.9, R equals 0.09, or R equals negative 0.09. Now, we already determined that the correlation is negative, so I know that it can't be either of the positive ones. Does that make sense? Okay, so I know it has to be one of the negative ones. And remember, in terms of correlation and statistics, negative does not mean bad, okay? Negative just means that as one is increasing, the other is decreasing. So they're going in opposite directions. Okay, now look at this data. Is it forming a pretty tight line? Or is it, like, not close at all? It's pretty close, right? So do you think that the correlation coefficient would be higher or lower for this set of data? Probably higher, because it looks pretty close to a line to me. So between 0.9 and 0.09, which one is closer to 1? 0.9. So my guess would be that the correlation coefficient would be negative 0.9, because it's negative, first of all, but it's also in a pretty close line. 0.09 would mean that the data is all over the place, and it's not very correlated at all. So if your data looks like it's forming a pretty straight line, then you're going to want to pick the correlation coefficient closer to the 1 or the negative 1, depending on if it's positive or negative. Does that make sense? Yes. Okay, so I'm going to have you guys with your groups discuss B. So all of my choices for B are 0.7, negative 0.7, 0.07, or negative 0.07. So let me just, hold on, don't start guessing yet. Let me show you guys A and B next to each other. Why do you think that all of my choices for A were 0.9 or 0.09, and all of my choices for B are 0.7 or 0.07? Because the data stops at 7? The data here stops at 7. What's the difference between A and B besides one is negative and one is positive? How, Jordan, can you say that louder? Yeah, you guys look at A. Do the data points look closer together in A than in B? Yeah, so that's why all of your choices here are 9, because they're closer together, so the correlation is stronger. Does that make sense? In B, it's still pretty linear, but they're a little bit further apart than they were in A, so that's why all of your choices for B are 7s and all of your choices for A are 9. Okay? So with your group, talk about B really quick. See if you guys can make a, come up to a conclusion as to what the correlation coefficient would be. I'll give you a minute. All right, guys, first of all, did you come up with, is this one positive or negative? Okay, so which two can I eliminate right off the bat? The negative one. Okay, so we either have 0.7 or 0.07 to indicate how tight our line is. How many of you groups voted for 0.7? How many voted for 0.07? Okay, why did you guys vote for 0.07? It's scattered. Is it very tight at all? Not really. So 0.07. Very good. Excellent. Okay, one more. This one should not be difficult, so I'll give you 15 seconds and we'll see who comes up with it fastest. Last one. First of all, tell me if it's positive correlation, negative correlation, or no correlation, and then which correlation coefficient would be the best representation. All right, how many groups voted for a negative correlation? How many groups voted for a positive correlation? How many voted for no correlation? Okay, good. So I'm going to write none. All right, so let's talk about it. If I have no correlation at all, remember, 1 and -1 indicate that it's a really strong correlation. So would R be equal to 1? Definitely not, right? If it was 1, that would mean that all of our data is in a perfect straight line, okay? So let's talk about the difference between 0.5 and 0.01. 0.5 would mean that it's pretty linear, but they're not very close together. Because remember what 0.07 was? It was pretty linear, but they're not super close together. 0.5 is bigger than 0.07. So it would be pretty linear, but not insanely close together. 0.01 would mean that they're not even close to being linear. So how many of you voted for 0.5? What about 0.01? Excellent. Okay. So do you guys see the difference between like something that has a negative strong correlation, a positive but it's not super strong, and then this one is none. So we should have the very smallest R possible for that. Not bad? A lot of your homework is just graphs like this, and you just have to pick which one goes. Okay? So that's estimating based off of information that is given to us. You also can calculate the correlation coefficient yourself. So I'm going to give you the formula, and we're going to do it by hand once. Okay? I know. It's going to be just like the other one where we're going to break it up into parts, except I don't have a handout for you. Okay, so here is your correlation coefficient equation. The correlation coefficient equation, we are going to break it up into parts, so don't freak out. But R is equal to the sum from I equals 1 to n. So basically, what this is saying is that I'm going to be telling you, you're going to be adding up all the data again, is essentially what it means. It means that we're going to start from the first piece of data all the way to the last piece of data. Of x sub I, so the first piece of data, minus x bar. Guys, what does x bar mean? The mean. So minus the mean times y of the first term minus the mean of all the y's, all divided by the sum from 1 to n, so of our first piece of data to our last piece of data, of the x minus the mean squared, square root it, and then times the square root of, from the first piece of data to the last piece of data, of the y minus the mean squared. This actually is less parts than the previous one, because we're going to be reusing the same parts, okay? So we're going to do this for a small data set. So we're going to do this for the data set -3, -3, 1, 2, and 3, 4. So that's the second example. So data set -3, -3, 1, 2, and 3, 4. Okay. Okay, don't freak out. Let's look at the different parts first. So I noticed that it first wants us to find, or part of our thing is going to be to find the mean. So let's do the means first, okay? So I'm going to set this up similarly to how your handout was set up that I gave you yesterday. So in the left-hand column, let's actually write the steps. So the first part that we're going to do is determine the mean. Okay, so we're going to determine the means first. Okay, I'm going to put the equation up. Okay. X bar means we're going to determine the means of just the X values. So that's going to be -3 plus 1 plus 3, yes? Okay, and then we're going to divide the whole thing by what? By 3. Okay, -3 plus 1 gives me -2, and -2 plus 3 gives me +1 all over 3. So my X bar is 1/3. Can you guys do Y bar for me really quick? So we're going to determine the mean of all of these Y values. Yeah, so did I. Okay, so I got Y bar, the mean of the Y value should have come out to 1. -3 plus 2 plus 4, divide all that by 3. That gives you 3 over 3, which is 1. Okay, so far so good? Okay, the next part is let's look at, in our formula, we have a whole bunch of differences, right? So let's do the differences. So let's write it as difference between data value and mean. Or data values and mean. Okay, so then we're going to look at all the differences between each data value and the mean. Okay. So let's do the x's first. So that would be, let's do the x sub i's minus the x bars. Okay. So we're going to do those first, and then we'll do the y's. So this means we're going to have a couple pieces of data. So let me underline this so we know what we're doing. The subscript I means that each individual piece of data. So when I equals 1, you're going to use the first piece of data. When I equals 2, you're going to use the second piece. I equals 3, you're going to use the third. So that means we're going to have to do this 3 times. Okay? So for the first piece of data, what is the x coordinate? -3. So the first one we're going to do is -3 minus the mean, which is of the x's, which is 1/3. That's all we're going to do. Okay? Now, can I subtract these just yet? No, I need a common denominator. If this is currently over 1, I would multiply everything by 3. So that would be -9 over 3 minus 1 over 3. So what would the first difference come out to? -9 minus 1. -10 over 3. Okay? Let's do the next one. What's the next x value? 1. So that's going to be 1 minus 1/3. Okay, what would 1 be with the denominator of 3? 3 over 3. Remember, this is times 3 times 3. So what's 3 over 3 minus 1 over 3? 2/3. Okay, and then the last one would be 3 minus 1 over 3. So when I multiply top and bottom by 3, that gives me 9 over 3 minus 1 over 3. And what does that give you? 8 over 3. So all you're doing is taking each individual x coordinate and subtracting it from the mean. So right next to it, what I want you guys to do right now on your own is do the same thing for the y's. So take each individual y coordinate and subtract it from y bar. Okay, this one should be easier because y bar was 1. Okay, so for the first piece of data, what did you guys get? -4. So -3 minus 1 gave us -4. What about the next one? 1. And the last one? 3. Okay, good. So you guys with me still? Okay, so what the next part that our formula wanted, so we just did in the numerator this part right here, each of those. They want us to multiply them together, so multiply each x difference and each y difference, and then add all of those products together. So let's write it in words first. So let's write it as product of the differences and we're going to then sum them up and sum. Okay? So we're going to find the product of the differences and then we're going to sum them together. Okay, so that means we're doing this part, the sum from I equals 1 to n. It's the same if you put it to the side than if you put it on bottom and top. Okay? Of xi minus x bar times yi minus y bar. So we're doing this part right now. Okay? So the product of the differences just means that we're going to take each x and y from each piece of data and multiply them. So the first one is going to be -10 over 3 times -4. So that's -10 over 3, times -4, plus, then we're going to do -2 over 3 times, or +2 over 3 times 1, plus 8 over 3 times 3. So we're going to multiply each x difference by its corresponding y difference and add them together. -10 over 3 gives me +40 over 3 times 2 over 3. 2 over 3 times 1 is 2 over 3, so plus 2 over 3. Plus, this is the same as 3 over 1, so 24 over 3. So when I add those all together, I get 66 over 3, which comes out to 22.